Hello and welcome. I'd like to talk to you today about some improvements in our performance testing infrastructure at MongoDB. Before I jump into that, I'd like to start with a story from a few years ago. So we have yearly releases, and this was after one of our yearly releases. And there'd been a regression reported by a customer on the new release. My boss's boss came and asked me about it. He asked me, did we know about this regression? And sadly, the answer was that we did know about this regression. We had detected it, and we had opened a ticket to investigate and try to fix it. What we hadn't done was fix the issue. We had released it without having fixed it. Now, why would this happen? Well, basically, the regression system was new at the time. And we get to the crunch of release, and it wasn't as trusted as some of the other things. And so we just never prioritized the ticket. When you get down to it, we've built software to tell us something. And in this case, we weren't listening to what it told us to. And when you build software and you don't listen to what it's telling you, that software is useless. Since then, we've done a lot of work and it's now a useful system. And in fact, we've gotten to a place where it is trusted, and so we've gotten into a good cycle that we're going to talk about. Our goal with performance at MongoDB is to understand the performance of our software and when it changes. We have lots of engineers working, making changes, adding the next big feature, adding performance improvements, and fixing bugs, constantly making changes. And we want to know when each of those changes go in, do they impact performance? Do they make it faster? Do they make it slower? And if they make it slower, we want to address it right away. We want to fix it and get that performance back. And the sooner we can do that, the better off we are. We can't always fix it. Sometimes you just have to accept a performance regression, say fixing a particularly nasty bug. And in that case, we want to understand the nature of the performance regression so that we can mitigate it as best we can and help our customers and users work around it. And sometimes things get faster. And when it does, we want to lock those performance improvements in and make sure that our users can take full advantage of it. So let me start briefly with the past, how we got to the base useful system that we've built on and that we discussed in this paper. So what we've done in the past was first, we automated everything. Our tests run in an automated system. They get scheduled based on commits. They run and they report results as part of our continuous integration system. No one needs to touch anything. We control the test noise as best we can. If you run computer tests, computer performance tests, you have noise in your system. They're giant randomness machines. You do that in a distributed system, it gets even harder to control. We've done a lot of work to control and mitigate that noise as much as possible. And finally, we've done a lot of work to be smart about how we decide when performance changes. So we're generating a lot of data. We have low noise data. We need to be smart about when we decide what to look at. We have a lot of test results, and we want to detect on any of them if they change and when. So doing something simple like saying, is there a 10% change, doesn't cut it. We've moved to very sophisticated techniques using change point detection to figure out exactly when the performance has changed. And these three things combined give us a useful system. And we've talked about all of those before. There's links at the end of this talk. So I'm not going to talk much more about them. But what they do is they start that engine flowing of we detect real things, engineers have learned to recognize that they're legitimate, and so they fix them, and they fix them quickly. Because they're fixed quickly, we have a more stable system, and it's easier to detect other things. And because the developers know that the system can catch things, they keep adding new tests. And so in this way, we have this engine of good making it easier for us to detect when the performance changes. The flip side of that is that we're using our system more and more constantly. And so we have a scaling problem that goes with it. We have more engineers committing more changes. At the same time, those engineers are adding more tests. So more commits times more tests. And we're also adding in more results for each one of those tests. And the end result is just a whole lot more to process. We're using signal processing and change point detection to find out where to look, but we still need a person looking at things to figure out, is this the important thing that an engineer should be spending their time on? And so we need to work to deal with that scaling problem. So to put some numbers on this, over the last 3 years, we've gone from about 12 commits on average a day to over 15, about a 30% increase in commits going in. So 30% just by itself as that first factor. Our test configuration's grown even more. We've tripled the number of configurations that we run. Not every task runs in every configuration, but we've more than quadrupled the number of tasks we run. We've more than tripled the base level of tests, and we have just almost 6,000 results that we could potentially measure now for every commit that's going into the server, every change that an engineer submits. So that brings us to the present. We have a useful system, but scaling is hard. How do we continue to scale this, and how do we improve our coverage so that we don't have customers telling us about regressions that we don't know about? So this paper focuses on 4 changes that we've made to support this. I'm going to go fairly quickly through this. So the first is we just got better at processing results. We went from having a rotating cast of people looking at the results to having a dedicated team. It allows for specialization. And then as that specialized team learns and gets better at it, they develop heuristics, and we bake the heuristics, well, we review the heuristics and bake them into the system to make everybody more efficient. And that way we're able to process more results and do a better job of it. We set out to do a better job controlling noise. We've done a lot of work. It's an ongoing problem. The change point detection algorithm tells us when things change. And we have a set of tests that should never change. We call them canaries. They test the performance of the underlying system as opposed to our software. And whenever they change, that's a problem, and we want to distrust the results that come along with it. So we can use some of the statistics that come from the change point detection to decide for each of these canaries that I just ran, do they seem reasonable for recent behavior? If not, we can throw the results away and run the test again. Great in theory. In practice, it turned out this didn't help us. We ended up rerunning too many tests, and it was just too expensive. We weren't able to focus it down well enough. We are likely to reuse some of the technology, and we may come back here, but for now, that one ended up being a negative result for us. All right, back to the positive. Adding more result types. When we started, we built up from nothing. And when you're building up from nothing, the easiest performance tests to run are just run a bunch of operations and see what the throughput is, return one result. Now that we have a stable system telling us useful things, we'd like better visibility into what's going on. We'd like to know what's the median latency, what are tail latencies, and we want to know if those change. So we built a lot of infrastructure to measure those and to aggregate them and to process them. And details in the paper, but it's really some cool stuff there. And it gives us a better sense of the dynamics of the system and the stability. And finally, the ability to compare arbitrary runs. The system as described so far is designed to detect when performance changes. So as time goes on, what changed? But sometimes we need to be able to look back across arbitrary time. For instance, when we're ready to release the next version of the server, we want to know not just what discrete changes we had, but what is the net impact of those. And so we need to be able to compare across those times. But we're dealing with upwards of 6,000 results with varying noise profiles. So we're able to leverage the statistics from the change point detection to do smart comparisons to see what is statistically different between now and then. And it really helps us give a better sense of where the performance really stands. So did these things help? That's the question. They all sound promising. Well, over the last release, we had more tickets. So recall when we detect a change and we assign it out, we create a ticket to track it. We had more tickets and more tickets per day. In fact, we had nearly twice as many tickets per day. And while we had more tickets, we resolved more of them by release. So that sounds promising. Are they high quality tickets? We grade the tickets. I grade the tickets. And the most interesting grade from this perspective is whether it was code related. So we bucket them to describe what they are. A code related ticket means that performance changed because of development to MongoDB, the server. It's not about a change to the test or the system. It's not noise. It's about the code. And that's gone up. So we have more tickets and they're higher quality tickets. This is goodness. What about the actual performance? So we're not able to fix every regression, and sometimes performance improves. What's happened there? So we have nearly twice as many performance improvements over this past release, a higher fraction, and it's gone from having an improvement once every 20 days to once every 9 days. That is great. And it wasn't accompanied with any increase in regressions. And keep in mind, a regression can be small, but if we measure it, we're going to count it here. So in absolute terms, regressions went down. In percentage terms, it went down. And it stayed at about 1 every 30 days or so. So we're detecting more things, they're of higher quality, and overall, we're improving the server more. So it really is working. We're detecting more changes, higher quality changes, more improvements. And that fits into this cycle. It really is working and making a difference on what the software that we ship to our customers. So that brings us to the future. Are we done? Of course not. And we view the future work that we have here, the continuing work, as a large optimization problem. And this is where you can come in. We really would love to leverage the community on this. So we're trying to simultaneously maximize signal to noise. So when the system reports something, we want it to be real and we don't want to lose things. We want to maximize test coverage. We don't want to find out from our customers. We want to find out ahead of time. So we want more coverage, more tests, more configurations, more everything. And we want to minimize the detection time. The faster we catch something, the easier it is to fix. All the while minimizing test cost. We don't have an unlimited budget. We have a finite budget. So we need to do all of these things without just burning a huge amount of money. And so a lot of the easy optimizations for these things trade each other off. You can maximize signal to noise by running every test 3 times instead of 1 time, but you blow out the test cost. You can reduce test cost by running tests less frequently, but then you're going to increase the time to detect and isolate things. We want to improve all of these at the same time, or at least multiple of them without hurting others. And we think there's ways to do it, and we want to work with the community on this. So you can help us, and hopefully we can help you. I've included a lot of links to what we've talked about. We're trying to describe our systems as best we can so you can work with real systems. We've open sourced things where possible. You can see tickets, you can see all the commits to our server. Our performance data is not open right now, but we're working to share it with academics. I've been able to share it with a subset of people. If you have an interesting problem, reach out to me and we'll see what we can do. And maybe in the near future, we'll be able to share data more publicly as well. We'll see. So thank you for listening to my talk. I hope that it was useful for you, and I hope I look forward to talking to you at the conference and your questions at the Q&A session. So thank you.